Hi everyone, today I will present my work on adaptive distributed stochastic gradient descent for minimizing delay in the presence of stragglers. This is joint work with Rawad Bitar, Parimal Parag, Venkat Dasari, and Salim Al-Ruwayh. So we are living today in the age of big data, and distributed computing is now present everywhere and has lots of applications. Sometimes this data is too large for one entity to process by itself, so we resort to distributed computing to make the computation tractable. The setting of distributed computing can also present itself naturally when the data that we would like to compute on is distributed among several devices like an Internet of Things, IoT. We also have distributed computing and cloud computing in many cloud-based systems. Amazon Web Services and Microsoft Azure can also be used by a user who wants to outsource a heavy computation task to the cloud. Another example of this setting is distributed machine learning, like federated learning, which is used by Google to train a machine learning algorithm across multiple decentralized edge devices who possess local data which they do not want to share between each other. The use of cloud for such applications can also present multiple challenges. In this talk, I will be focusing on distributed machine learning and some of the challenges that are associated with it. So consider a setting where a master wants to run a machine learning algorithm on a large dataset A. If the dataset is too large, then the learning process can become computationally intractable. So the master can outsource the computations to the worker nodes by distributing the data among them in order to make the learning process faster. The main challenge in this setting that I will focus on is the straggler problem. Stragglers are slow or unresponsive workers that can significantly delay the learning process. The reason these stragglers can delay the process is because in this setting, the master needs to wait for all workers to complete their local computations. So here, the master is as fast as the slowest worker. For that reason, in this work, we are interested in developing techniques that speed up distributed machine learning in the presence of stragglers. The setup that we will be considering is the following. The master has a dataset X of size M and dimension D and a set of corresponding labels Y. The master wants to learn a model W that best represents labels Y as a function of the dataset X. This can be expressed as an optimization problem where we want to find a model W star that minimizes a certain loss function F. When the dataset is large, meaning the number of data vectors M is large, solving this problem may be computationally intractable. What the master can do is recruit workers and distribute the data to these workers. Here, the matrix A represents the concatenation of X and the labels Y. The data partitioning is done horizontally, so each worker receives a certain number of data vectors, meaning a certain numbers of rows in the matrix A. The workers can now compute on their local data and push their computations back to the master. The master then aggregates the received computations and updates the model. This can happen through several iterations, for instance, if the master is running an iterative machine learning algorithm such as gradient descent. One popular solution for the optimization problem which I just described is in fact gradient descent. Suppose we want to optimize a certain objective function given by the curve shown here. What we do is we start at a certain point of this curve and then we make small steps in the direction of steepest descent. This corresponds to initializing a certain model W0 and then performing the following update at each iteration. The update is wj plus 1 equal wj minus eta nabla of f, where eta is the subsize and nabla f is the gradient of f. One problem in gradient descent is that when the dataset A is large, the computation of the gradient is cumbersome. Stochastic gradient descent is a variant of gradient descent where at each iteration, the gradient is evaluated at only one data vector that is chosen uniformly at random from the dataset. So at each iteration, we sample one row uniformly at random from the dataset A and update our model based on that vector only. What is effectively happening here is that we're using a noisy version of the true gradient instead of computing the full gradient. The main advantage here is compared to gradient descent is that computation of the gradient at each iteration is significantly simpler because the gradient is evaluated at only one point. It is also possible to relax SGD by taking a certain subset of uniformly random points at each iteration This is known as batch SGD, where the subset taken at each iteration is of size S. It has in fact been proven that both SGD and batch SGD can converge to the optimal solution, but the disadvantage here is that they would require a higher number of iterations. SGD, as many of you may know, is the backbone of many machine learning systems nowadays. For that reason, we are interested in techniques that speed up distributed stochastic gradient descent. But first, to understand how gradient descent works in the distributed setting, consider the following scheme. Assume the data is partitioned across the workers and we want to run distributed GD. The update procedure is the following. At iteration j, the worker sends the latest model wj to all workers. The workers then compute the partial gradients on their local data, which are g1, g2 up to gn. Then the workers can send these partial gradients to the master. The master can now obtain the full gradient by summing up the partial gradients. This simple aggregation by summation of partial gradients works when the gradient of the loss function is additively separable. One example where this works is the L2 loss function. For other loss functions, the aggregation procedure may not be trivial. As I previously mentioned, this setting suffers from stragglers, who are slow or unresponsive workers. Here, the master needs to wait for all workers to obtain the full gradient, so he is as fast as the slowest worker. Several works in the literature propose techniques to alleviate the problem of stragglers and distributed gradient descent. A line of work which was started by Tandon et al. In 2017 proposed using coding theoretic techniques to provide resilience against stragglers. This approach was called gradient coding. The high-level idea of this approach is to distribute the data redundantly among workers, and the workers would send an encoded version of the partial gradients. Responses from stragglers would then be treated as erasures, and the full gradient is decoded by the master from the responses of non-stragglers. Another line of work in the literature proposed ignoring the responses of the stragglers and obtaining an estimate of the gradient rather than the full gradient, which is essentially what we do in single-node stochastic gradient descent. One simple way to implement this is to partition the data and distribute it to the workers with no redundancy, and then at each iteration, the master waits for the responses of the fastest k out of the n workers and ignores the responses of the remaining n minus k stragglers. We call this approach fastest k SGD. This is in fact equivalent to batch SGD if the response times of the workers are random IID and independent across iterations. Through this equivalence, it can be shown that fastest k SGD can converge to the optimal solution. Some works also considered mixed strategies which combine both coding theoretic approaches and approximate gradient computation. In our work, we focused on speeding up fastest k SGD as a building block to the general problem of speeding up distributed machine learning. The question that we ask in our work is how to choose the value of k in fastest k SGD with fixed step size. To understand why this is an important question to answer, consider this example, which shows the error as a function of time when fastest k SGD is run over synthetic data for multiple values of k. The blue curve shows the error when the master waits for the fastest 10 out of 50 workers in each iteration. As you can see, the error in this case decreases quickly in the beginning because the time per iteration here is short compared to the cases of k equal 20, k equal 30, and so on. After the initial decrease, the error hits a plateau where it does not improve any further. It is intuitive that the error floor for k equal to 10 is higher than others because the gradient estimate that is obtained for k equal to 10 is noisier than other cases where k is larger. So the key observation here to notice is that there is an error runtime trade-off. In fact, convergence is faster for small values of k in fastest k SGD, but the accuracy of the model is lower because of the higher error floor. So what does theory say about this? It is in fact well known that SGD with fixed step size goes through an exponential phase where the error decreases exponentially, then enters a stationary phase where Wj oscillates around W star. You can in fact notice this phase transition in the graphs. First, we have an exponential decrease in the error, and then at some point, the error hits a plateau and starts oscillating as we approach the stationary phase. Fastest KSGD has been studied by Botu et al. And Dutta et al. For a predetermined fixed K, but the problem of the optimizing the error runtime trade-off in terms of K has not been yet studied. In our work, we speed up distributed SGD in the presence of stragglers by optimizing this trade-off, meaning we want techniques that achieve lower error in less time. By looking at the graph shown before, what we really want to do is to hit the envelope of these curves in order to get the best of all worlds. Our contribution here is a novel algorithm, which we call fastest KSGD. The main idea is to adapt K throughout the algorithm to maximize time spent in the exponential decrease. This in turn will maximize the convergence rate. What we do is we start by small k, and then when the error hits a plateau, we increase k, meaning we increase the number of workers that the master waits for. We repeat this process of increasing k every time we detect a phase transition until we reach the maximum value of k. However, this is easier said than done because in practice, we do not know the error because we do not know the optimal value W star. Our results here are twofold. First, we have theoretical results where we derive an upper bound on the error of fastest KSGD, and then we derive the bound optimal switching times, meaning the times at which the master should switch from waiting to K workers to waiting to K plus 1 workers. And then we introduce a practical, realizable algorithm for adaptive fastest KSGD that is based on a statistical heuristic. Here, the first theorem, using techniques from the Newell theory, we upper bound the error as a function of time, and then we derive the corresponding bound optimal switching times. To understand these results, consider this example where we plot the error in Theorem 1, and then we use the result in Theorem 2 to optimize the error runtime trade-off. As you can see, the adaptive dotted version of the curve hits the envelope, and hence optimizes this trade-off and can reach lower error in less time. Now, moving to the practical algorithm which we propose, the main idea here is the same. We start with the smallest k, since it gives the fastest decrease in the beginning, and then every time we detect a phase transition, we increase k. Now, the challenging part is detecting this phase transition, since we do not know W star, so we do not know the error function. What we do to detect this phase transition is we monitor the sign of consecutive gradients. In the transient phase, due to the exponential decrease in the error, consecutive gradients are likely to point in the same direction, meaning their dot product is positive. However, in the stationary phase, due to the oscillation, consecutive gradients are likely to point in opposite directions. We use this as a basis for our decision on whether the phase transition has occurred or not. This idea was proposed by P. Flug in 1990 as a general stochastic approximation, and then was used by Chi and Toulis in 2018 to detect a phase transition. Detecting phase transition serves many purposes, such as terminating the SGD algorithm or using different techniques to improve the error. In our work, we use this idea to devise an adaptive fastest K SGD algorithm. What we do is we monitor the sign of consecutive gradients by counting the number of times the dot product is positive and the number of times it's negative. Namely, we initialize a counter and update it throughout the runtime of the algorithm, where we increment the counter by 1 if the product is positive and decrement it by 1 when it's negative. At first, we expect positive products due to the exponential decrease. Then at some point, as we approach the stationary phase, negative gradients will start accumulating. When the number of negative gradients surpasses the number of positive gradients by a certain threshold, we declare a phase transition and we increase the value of k. This means that every time we detect a phase transition, the master starts waiting for the responses of more workers in order to keep improving the accuracy of the model. And we keep repeating this until we reach the maximum value of k. Here, I will show you some simulation results quickly. We have implemented this algorithm. The loss function that we use here is the L2, and the response times of the workers are modeled as IID exponential with rate 1. We consider a setting with 50 workers where the data set consists of 2000 data vectors of dimension 10, and we used a fixed step size. The graph shows the error as a function of time for adaptive versus non-adaptive versions. it is clear that the adaptive version enables reaching lower error in less time. Namely, notice that the adaptive fastest k SGD reaches its lowest error at approximately t equal 2000, whereas the non-adaptive version reaches the same error only for k equal to 40 at approximately t equals 6000. These results confirm our intuition and previous theoretical results. This work is relatively new. We are also actively working now on implementing this on real data on data sets such as MNIST and C4. We have also compared this to the asynchronous gradient descent, and the results showed that the adaptive fastest KSGD is as fast as the asynchronous in the beginning, but it reaches a better accuracy towards the end. To conclude, in this work, we focused on the straggler problem, and we introduced the adaptive fastest KSGD. We have theoretical results and a practical novel algorithm that is based on a statistical heuristic. The numerical results show a gain with respect to non-adaptive SGD. In terms of future work, we want to implement this on real data, as I previously said, and we want to consider variable step size, and we want to consider mixed strategies where we combine the coding theoretic techniques with the adaptivity idea that we introduced in this work.